So before going into my talk, let me briefly introduce who we are and what we do at Iontas. So we are an antibody drug discovery company formed in 2012, which is a few years ago. And our strength lies in our antibody capability using phage display to generate antibodies that are very specific and potent to targets that are normally difficult to other technologies. But most of that work is confidential. We do that for our clients. So what I can talk about today is the technology development we do at Iontas, specifically KnotBodies to target ion channels. So targeting ion channels, I don't need to tell you how important they are because they are involved in multiple diseases, and they normally are a target class for small molecules. But as you know, most of the existing small molecules of ion channels have a number of disadvantages like lack of specificity, dose-limiting side effects, and possibly lack of efficacy in patients. So this opens up a huge opportunity for antibody companies like us because antibodies have the reputation for being potent and selective. So you will hear these two words quite a lot in my talk, just like you heard strong and stable in the recent elections. So sorry about that. But having said that, if you look at the history of antibody development against ion channels, it's not a great story. After spending several millions of pounds over the last 15, 20 years, there are hardly any functional antibodies to ion channels. So there are several reasons for this, and I will get into that. And one of the reasons is that antibody generation campaign requires good quality antigen to do immunizations or phage display or screening. And as you know, ion channels are very difficult to produce. Even if you purify them, they are very low stable to last for a while. Then the other reason is that antibodies normally have a flat binding surface, and they bind to epitopes that are outside the plasma membrane. And especially if you look at this picture, and if you're working with the voltage-gated channel, there is very little epitope that are available outside the membrane, and which antibodies cannot target. So even if you go through all this trouble, make a binder that may not necessarily the functional blocker you are looking for, because ion channels are quite dynamic molecules, and the binder you made may not be to the right conformation. So we have all these troubles. And because we are a small company, we don't have the resources to do a brute force approach. A lot of big pharmas do, screen more. If you don't get a blocker in 1,000 clones, they screen 10,000. It's not something we can afford to do. So we have to do something different. And we decided to look into nature and see what the nature does. So in nature, there are several thousands of venomous species make ion channel blocking compounds and use it against predators to avoid getting eaten, or used against their prey. The few examples are given here. There is this SHK molecule toxin that's produced by a sea anemone, which blocks Kv1.3, and then the tarantula venom that has a toxin which blocks 1.7, and similarly an acid blocker from black mamba and calcium channel blocker from corner snail. So if you look into the detail of these toxins, they have several shared characteristics. Mostly, they have 30 to 40 amino acids, which might make you think they are peptides, but technically they are not, because unlike peptides, they have a very well-defined three-dimensional structure. And this structure is further conserved by a three or four disulfide bonds that makes a special fold called inhibitory cysteine knot. And that's where the name knottin comes from, and I will use that term to refer to all the toxins from now on. So even though these toxins or knottins have a high structural similarity, they all have very different sequences and modulate different functions. For example, you can see 3 different toxins that more or less have the same structure from 3 different sources and block 3 different families of ion channels. And they're also found in a lot of non-venomous species, such as plants, doing non-ion channel modulating functions, such as protease inhibition, anti-malarial activity, antibacterial activity, etc. Then there's also a history of using these toxins or knottins as therapeutics. For example, cyclotide or Prialt is an approved drug for the treatment of chronic pain. And it is the active molecule in this drug is a chronotoxin that blocks N-type calcium channels. Similarly, delasatide is an engineered version of SHK toxin from sea anemone that blocks Kv1.3. It's currently being trialed for the treatment of psoriasis at phase 2. But if you just forget these exceptions, most naturally occurring toxins lack the specificity that required from a therapeutic, because these are molecules that are evolved to paralyze prey, not to cure your pain or cancer or arthritis. So most cases, they need further engineering to be used as a therapeutic. But the idea of engineering a knottin and use it for multiple therapies has been there for the last 20, 25 years. But there is not that much success, and it's mainly because these are really difficult molecules to engineer. For example, a knottin is not amenable to phage display, a technology that allows you to handle large libraries of billions of variants and pick the molecule with the specificity you're looking for. It's because phage display requires proteins to be folded correctly before it gets packed into the phage. And these multi-disulfide proteins are very hard to fold correctly for a prokaryotic organism. Then if you decide to go for a rational approach, there's only a limited number of molecules you can make and test, because again, these multi-disulfide proteins are very expensive to synthesize and they're very complex. And also the rational design strategies don't give you much control over what you get on the other side. You make one and test it and see the result. So again, if you go through all these troubles and make a specific molecule, then they have the problem of short half-life. Most of them have a half-life of a few minutes to hours because they're small and they get through the renal clearance. And such short half-life is too short for a molecule that is actually expensive to synthesize. So just to summarize, knottins have a great potential to be ion channel blockers, but they lack from specificity, and they have short half-life and also very difficult to engineer. On the other hand, antibodies have a large binding surface, which could give you the specificity you're looking for, and they are amenable to all kind of display technologies which allow further engineering. And they also have a long half-life of 3 to 4 weeks, which a knottin or a toxin does not have. So that's where the concept of the KnotBodies comes in. So where we want to combine the best of both worlds to make specific, engineerable, long molecule with long half-life. So what we decided to do was take one of the antibody binding loops, which is not that important for binding, replace that with a knottin or an ion channel blocker, and use rest of the antibody binding loops to engineer the specificity and the potency you're looking for using phage display. So in the first instance, to prove the concept, we took a plant knottin called EETI, which is a trypsin inhibitor. Okay? The reason we chose this was, trypsin is a much easier target to work with than ion channels, and we can buy a lot of trypsin for absolutely nothing, and for all our screening and selection. And by doing that, we can make sure we have a solid platform technology before moving on to something as difficult as ion channels. And because all these molecules are very similar structure, we can easily replace this boring trypsin knottin with an ion channel toxin later on. So that was the concept. So these slides will show you how we did this. How did we insert an EETI knottin into a VL CDR. So for engineering and phage display purposes, we did not use the full antibody, as you can see here. We only used the business end of the antibody, which contributed to the binding, which is the VH and the VL domain. And this VH and VL domain has got 6 binding loops called CDRs. CDR 1, 2, 3 on VH and 1, 2, 3 again on VL. But not all these binding loops are equally important. For example, the main binding pocket is made by the VH and VL CDR3, the center. Okay? And we didn't touch that. We went on to something that is peripheral and the least diverse to insert a knottin in. We also anticipated that if you just take a knottin and put directly into an any VL sequence, it might actually affect either the folding of the knottin or the functionality of the knottin or the folding of the antibody itself. So what we did was we used a library approach where we took a knottin with a random linker on both sides and put into a library of light chain sequences. So we put a library into another library and use phage display for finding the right molecule with the function as judged by the trypsin binding. So for anyone who's not that familiar with phage display, I will briefly explain how phage display works. So in phage display, we fuse the protein of interest, here the antibody in the VHVL format, to gene 3, which code for a code surface protein called P3 on the surface of phage. And when we make phage from a bacteria containing this vector, the phage will have the antibody displayed on the phage as a P3 fusion and the gene that is encoding the antibody inside the phage, which creates this crucial genotype-phenotype linkage that's important for any kind of selection system. So once we have that, we can now select for the phenotype, which is the antigen binding, by something called panning. So in panning, what we do is that we immobilize antigen on a surface, allow the phage library to bind, and wash away any non-specific binders, elute the phage antibody, and recover the gene that's responsible for the binding. And we normally do 2 to 3 rounds of this to get specific binders. And we routinely sample libraries containing billions of variants in a span of 2 or 3 weeks. So it's a very solid technology we use routinely at Iontas. So in this case, we did the same to get the trypsin binding KnotBodies. So after a couple of rounds of selection on trypsin, we just looked at the polyclonal phage to see if everything is going all right. And the first thing we noticed is that suddenly a knottin can be displayed on phage when it's part of an antibody. But you cannot do that when it is directly fused to the phage, as a lot of people do. And it's a very significant result because most knottins don't efficiently display on phage. I spent my entire PhD trying to find a way to get it on phage, and this was a quite nice result for that. And the significance is that now suddenly this is engineerable. We could do all the things we normally do with antibodies and phage display to get the specificity or affinity we can do. So we also did some monoclonal analysis and find a lot of KnotBody binders that from both CDR1 and CDR2, which retain the trypsin binding. And we also shown that this trypsin binding actually come from the knottin, not from the variation we introduced either in the linker or in the antibody sequences, which is also possible from phage display. By taking the trypsin binding loop of the knottin, mutating the key residues, which is a proline and arginine in the loop 1, to a glycine and alanine. And when we did that, all the KnotBodies lost binding, showing that the binding actually come from the knottin, not from the antibody linker or antibody. So we also went on to show that that library approach we used to select the linkers is very important. So we took 2 KnotBodies and replaced the phage display selected linker with a glyphosine linker or a glyphosine linker, multiples of it, which most people use whenever they fuse 2 proteins, and we lost binding. So it was quite important to do that in a laborious phage display library approach to get the correct molecule. We also went on to solve the structure of these KnotBodies, 2 of them one at 2.5 angstrom, another at 1.95 angstrom. And the structure clearly showed that both antibody and the knottin is correctly folded. And you can see here in the middle, it's an overlay of an existing knottin crystal structure to what we see in the antibody, and it's completely overlays. And this is just an antibody, a standard antibody, which will look like the same. So we created something that folds well, not a monster that completely misfolded. So in the next few slides, I will show a few capabilities of the KnotBody scaffold. The first one is, so far, we have a knottin in the light chain giving all the function, which is paired with a heavy chain that do not do anything. So now we want to involve the heavy chain to do something. First of all, we want to show we can improve the binding of the existing molecule. Second of all, we want to show that we can select a new heavy chain that can make a bispecific molecule. Thirdly, we also want to show that we can alter the specificity of knottin that's currently in the VLCDR completely to something else by loop diversification. And finally, we want to do the interesting bit, which is replace the trypsin binding knottin with the ion channel blocking toxin to create ion channel blocking antibodies. So here's the first capability I talked about. What we did was we took that trypsin binding light chain KnotBody, paired with the 10 to the 9 different heavy chains, and did phage display selection on trypsin under conditions that favor enrichment of higher affinity clones. And in this ELISA graph shows most of the new binders with the new heavy chains bind better than the parent, which are shown here. And we also shown that the improved variants have a higher or a better Hoff rate compared to the parents when we do an SPR. Similarly, we also created bispecific molecules by pairing that light chain KnotBody with a library of heavy chains and selected against 3 different targets. As you can see, the parent KnotBody bind to the trypsin through the VL, and the new bispecific KnotBodies engages VH to bind to 3 different antigens. And finally, we also shown we can modify the trypsin binding loop within an antibody to completely something else and create new binders. In order to do that, we took the trypsin binding loop, completely randomized it, changed the loop length to different 6, 9, 8, or 9 amino acids, and did selection on 2 different antigens and got binders, multiple binders to it. And the sequence logo shows the binders we generated, and you can see the sequences as very, very different from the original loop 1 sequence, which gives a trypsin binding, and they're different in amino acid composition. They're also different in the length. And finally, to some ion channel work, and I might be running out of time for that. And so, to do as an first ion channel target, what we chose was KV1.3. KV1.3 is a well-validated target in the treatment of autoimmunity. So, in autoimmunity, the autoreactive T cells are heavily dependent on KV1.3, while the other cells, such as memory cells or knife cells, are dependent on KCA 3.1. That's the data that's available to us. And the rationale is, if you can take out the autoreactive T cells using a selective inhibitor of KV1.3, you can treat autoimmunity without causing a blanket suppression. So what we did was we took two well-known toxins that bind to the KV1.3 through its spore. One is SHK and another is calliotoxin, and used to replace the trypsin binding knottin at the VLCDR2. And we made them as IgGs and used QPatch to measure the blockade of the current. And these are some nice dose responses, where the KnotBody SHK has an IC50 around 9 nanomolar, and the calliotoxin KnotBody has an IC50 around 430 nanomolar for KV1.3. We also went on to do some PBMC assays to show this KnotBody is actually functional on T cells by putting them onto PBMCs that are activated by CD3, and suddenly they inhibit the cytokine and granzyme B inhibition by these PBMCs, so the function is preserved. Similarly, we also made some ASIC blocking KnotBodies by taking a salmotoxin, which is a toxin from tarantula that block ASIC1 specifically, and we put that onto 2 different antibodies, and you can clearly see that they block ASIC1 with good IC50s. So, to summarize, we can create ion channel blocking KnotBodies by doing what nature does. Taking a toxin that is non-specific and hard to engineer and put in an antibody which is actually have a long half-life and engineerable. And by doing so, the knottin gets a half-life of an antibody, and antibody get the functionality of the knottin. In short, we use these KnotBodies where the function, the ion channel blocking function comes from the toxin, and the half-life and the specificity come from the antibody. We can also use it in different contexts. We can use it as a biospecific, and we can also use it just to engineer the toxin itself. And this is the acknowledgement slide. The different people who worked on this. Damien Bell, who is here, did all the electrophysiology. Sachin Sured did all the crystallography and structural biology. And these are the people who helped me at other various points. And Sophion has been great for us, setting up the ion channel lab at Iontas. And also, the ASIC work I shown is done by Naya at Sophion. Sorry, this has been a talk heavily on protein engineering. Maybe next year I will have more ion channel data because we are slowly moving into it. And thank you for your time. I'm happy to take any questions.
Thank you, Aneesh. An exciting presentation. Any questions?
Right, so you didn't share any PK data, but can you tell us about it? Did it show the same sort of clearance as an antibody, or did the peptide get cleaved off the antibody at all?
We haven't done any PK at all because we haven't got that far. We are mainly focusing on getting the technology up and running and making solid. But one thing we know from size exclusion studies is that once it's been produced, we use it as a genetic fusion and express in CHO cells. And once it's produced, it stays as one piece. It doesn't really get degraded even over a long time. So we hope that it will stay like that, and it will behave like an antibody and have a long half-life. But we don't have any solid data to show that.
How does the potency of SHK in your KnotBody compare to SHK applied to the cells by itself? And do you have a negative control, perhaps, where you've used an inactive toxin, knottin mutant,
yes,
in the same antibody scaffold?
Yeah. So to answer the question, so SHK has a reported IC50 around 20 picomolar. So we see around a 500-fold drop in potency. It's something people saw whenever they do anything with a toxin and add something to its back, even a peg. It's not a big problem for us because the original toxin is so potent. We have the room to lose a bit of potency. And so far we haven't used this antibody CDRs at all to further improve anything. So even if we lose something, we can build it back using the antibody, which we haven't done it so far. So the second question about negative control. All the assays been done against negative control, which the antibody background is the same, but the knottin or the toxin is actually the trypsin binder, which has the same fold, and none of them actually block Kv1.3. So it's not a rundown or anything, it's a true blockade through Kv1.3, so through SHK or calliotoxin. And we have several other toxins I cannot talk about because we haven't patented them, and some of them are really good, better than this, and probably one specific.
What about cost? What's
Cost? Cost of doing this?
The cost of, comparable costs with a normally available antibody or normal antibody production.
I think so far these KnotBodies express as well as an antibody. Okay, if it might be different from toxin to toxin. We haven't sampled that many, but if it's significantly reduces expression, it will be higher cost. But if you hope we can keep the same expression normal antibodies in our system, it expresses as well as other antibodies. So the cost will be similar to other antibodies.